Hi, welcome back to Electronic Structure and Bonding. My name is Kevin Tokoph. Make sure to like this video and subscribe to the channel for future videos and notifications. Alright, so in the last few videos we've been calculating crystal field stabilization energy. However, we've been doing it for octahedral complexes. And we know hopefully that octahedral complexes have the general form of a metal, and then we have some ligand, and there's going to be 6 of them, and then some charge. Okay? Look at this one. This one only has 4 ligands, and we are going to assume it's tetrahedral because generally when we calculate crystal field stabilization energies, we're either doing it for octahedral or tetrahedral at this level. So we are going to assume this is a tetrahedral. This is a tetrahedral complex. Now, several things to remember about tetrahedral situations of calculating crystal field stabilization energy. Whenever I was doing octahedral, I always had the E sub g on the top and T2g on the bottom like this. It turns out that for tetrahedral, it's flipped, okay? The T2g is on the top and the E sub g is on the bottom, okay? It also turns out pretty much everything is flipped. This right here is the degeneracy level, okay, degenerate energy level. This difference in energy right here, this is 3/5. The 3/5 was on the top last time because E sub g was on the top. But now it's not delta octahedral, it's delta tetrahedral, okay? And just like it was 2/5 on the bottom in octahedral, now this difference in energy is 2/5. But again, it's delta tetrahedral, all right? So hopefully that makes sense. That's basically the first thing to remember about tetrahedral complexes. The second thing, which makes it a little bit easier, to be perfectly honest, is the fact that you don't have to determine if something's high spin or low spin, because for tetrahedral, they are always high spin. And when we do the example, we'll again go into what that means, particularly the high. So that flow chart we've been using in the past few videos, we don't need that for this. They're always high spin. Now what we do have to do is, again, step 1, what we did in the last video, in the last few to be perfectly honest, is we have to calculate the charge on the metal, okay? This one's a little bit more challenging because overall the charge is -2 and our ligand has charge. So what I do is I set the overall charge of the complex equal to the sum of the individual charges. Chloride always has a -1 charge, okay? And then there are 4 of them, plus the charge on the nickel. All right, this is going to be -2 is equal to -4, oops, too many of those, -4 plus nickel. So I add 4, this cancels, so nickel is going to be having a +2 charge, or I can write this as nickel 2 plus. All right? Nickel 2 plus. My next step is I need to calculate the number of d electrons. All right? Let's go to nickel. Nickel is right here. If it loses 2 electrons, how do I know it loses 2? Because it has a 2 plus charge. If nickel loses 2, it's going to preferentially lose these 2 first. So it's just going to have 1, 2, 3, 4, 5, 6, 7, 8 d electrons. Okay? 8 d electrons. Now I have to remember, I'm going to now fill in the electrons. It's high spin, so number 1, there is no pairing energy. But I'm going to do high spin. So what does that mean? 1, 2. Instead of staying down here for 3 and 4, I'm going to go up high because it's high spin. 3, 4, 5. And then I'm going to come down 6, 7, and then 8. Okay? So that's high spin. All right? Now I need to calculate the crystal field stabilization energy. So what am I going to do? Well, my crystal field stabilization energy is going to be, I'm going to use this first, 3/5 delta tetrahedral times the number of electrons in that area, which is going to be 4. Okay, those orbitals, 4 electrons, minus 2/5 delta tetrahedral times the number of electrons in that area, or those orbitals, that is 4. All right, so what is this equal to? And I don't have to worry about the pairing energy. This is going to be 12/5 delta tetrahedral minus 8/5 delta tetrahedral. So overall, it looks like that is going to be 4/5 or 4/5 delta tetrahedral. All right? So that is going to be right there in my crystal field stabilization energy for this tetrahedral complex. All right, here's an interesting thing. Suppose it's tetrahedral, but I want to calculate the delta octahedral for this, or at least I want to compare it to that. Well, I have a general rule of thumb, and it's that delta tetrahedral is approximately 4/9 of delta octahedral. All right? So how do I convert this into a delta octahedral for a comparison? Well, I'm going to take 4/5, and I'm going to substitute this expression for delta octahedral, this right here. I'm going to plug in this because it's equal to delta octahedral. So this is going to be 4/9 delta octahedral. So I'm getting that this is, at least relationship-wise, is going to be 16/45 delta octahedral. And that's the same thing as 4/5 delta tetrahedral. All right? So that's going to be a direct comparison of them. The key here and the point is just that delta tetrahedral, the difference in energy that you see in this tetrahedral complex, is going to be less, approximately half of that of delta octahedral. Okay? So just to make that clear. All right? And that's all there is to the tetrahedral complex. It's always high spin, and then you just have to remember the crystal field splitting diagram is flipped upside down to where EG in the 3/5 is on the bottom and T2G in the 2/5 is on the top, and then instead of delta octahedral, you are specifically dealing with the delta tetrahedral. And then you calculate crystal field stabilization energy in a similar way. And it's in terms of delta tetrahedral, not directly octahedral. All right? So hopefully that made a little bit of sense. Make sure to like this video and subscribe to the channel for future videos and notifications. Thank you very much.